Since the 1990s, emission control technology has developed continuously in Europe in response to the European environmental directives, otherwise known as the Euro directives. The function of all of these directives is to control polluting gas emissions in all new vehicles sold in the European community. The directives also establish the maximum levels of emissions allowed during the periodic tests to which all vehicles driven in Europe are subject. The implementation of these directives has involved important technological changes in vehicles over the years, and especially the creation of more efficient, cleaner engines through the use of more sophisticated emission control systems. In the last 2 decades, there has been a dramatic technical evolution of emission control systems for cars, and this technological leap has been most noticeable in diesel engines. In 1992, when the Euro 1 directive was introduced, the exhaust system of a standard diesel vehicle was only made up of 2 or 3 silencers. It was a highly rudimentary emission system that did not contain any active element to treat polluting gases. This is because these were not necessary to remain below the maximum polluting gas limits established by the directive. Their sole purpose was to maintain acceptable counter-pressure levels to ensure that the engine worked properly, while reducing the engine noise to the legally established levels. The years rolled by, and in 1996 the Euro 2 European directive came into force. This significantly restricted carbon monoxide emissions, making it necessary to include oxidation catalytic converters in exhaust systems. These catalysts need to reach a minimum activation temperature of around 300 degrees centigrade to work, so they are placed close to the exhaust manifold outlet. Four years later, Euro 3 came into force in 2000. This directive cuts back the maximum carbon monoxide CO limits once more by separating the values of nitrogen oxides NOx and unburnt hydrocarbons HC for the first time, in addition to reducing the maximum limit allowed for solid particle atmospheric emission once more. This regulation ensures that the gases begin to be measured as soon as the engine is started, and not 40 seconds later as before, forcing manufacturers to build more refined injection systems in order to meet the requirements. The first lambda probes began to be seen in diesel vehicles. With the Euro 4 European directive, the carbon monoxide, unburnt hydrocarbon, nitrogen oxide and solid particle limits are significantly reduced once more, making it necessary to introduce more modern and efficient management technologies. These changes brought about the massive implementation of the EOBD2 systems, which include catalyst output monitoring systems. To do this, the broadband lambda probes were brought in to manage fuel-air mixtures much more efficiently. At the same time, the use of the second lambda probe on the catalytic converter output became standard as an item used to monitor catalyst performance through the oxygen consumption produced by the oxidation reactions occurring inside. Four years later, in 2009, the Euro 5 directive was enforced, which particularly stresses the significant reduction of the emission limits of the solid particles travelling in exhaust gases. To achieve this ambitious target, diesel particulate filters, or DPFs, appeared in order to retain the solid particles in their filter and to periodically burn them and turn them into carbon dioxide. It must be said that although the Euro 5 official directive came into force in 2009, most manufacturers were already fitting DPF systems in their vehicles before this. The DPF was first used as standard equipment in 2001 by the PSA Group in the Peugeot 607. The Euro 6 directive will be coming into force in 2014 and will focus on drastic reduction of harmful nitrogen oxides that cause acid rain. Modern emission control systems have therefore been developed, such as the SCR, Selective Channeling Reducer Systems, using urea to tackle nitrogen oxides. These systems are known on the market as SCR systems with AD Blue. The systems turn the nitrogen oxide molecules into water and molecular nitrogen, N2, which is harmless and accounts for 78% of our atmosphere. To do this, AD Blue, a compound made up of 34% urea and 66% water, is injected into the exhaust pipe just in front of the mixer ring located on the inlet of the SCR catalytic converter. This ring plays an important role, ensuring that the molecules of the AD Blue reducer liquid are blended evenly before they go into the SCR reduction catalyst, so that the reaction is as efficient as possible. As we have seen, the exhaust system has evolved significantly in just 2 decades. From being a mechanical system of scarce technological complexity to one of the most technologically advanced systems in our modern vehicles. This evolution has also meant a significant price hike due to the difficulty of repairing such systems, which makes more obvious the need for ongoing quality technical training to provide full guarantees in maintaining this technology. Walker is one of the world leaders in designing, developing and implementing these systems, both for original equipment and the aftermarket. We have therefore produced this brief summary video to show all of these technological changes to those of you who are interested. We at Walker hope that you have enjoyed it and that it gives you a better understanding of the evolution of these important automobile systems.
We are Garage Gurus. Join our community. Follow us on social media. Thanks for watching this video. The video description contains all the relevant links. Don't hesitate to like, subscribe, and be notified when we post new content. Also, check out our Garage Gurus online course catalog.